All right, in this video, I'm going to go through the series review. So let's get started with number one. I want to find the 10th partial sum for this particular series, which means I need to find the sum of the first 10 terms. So my first step would be to identify if this is an arithmetic or geometric series. Now, from 28 to 34 to 40, I think it's pretty clear that we're increasing by 6 each time, right? Plus 6, and so on and so forth. So I think this would be best represented as an arithmetic series. Remember, one of the formulas we could use to find a partial sum of an arithmetic series would be the sum would be the number of terms n times your first term plus the last term divided by 2. So that could be one of the formulas we use here. Or if we set this up in sigma notation, we could just find what the general term looks like and sum it from n equals 1 to 10, and both of those would have the same effect. So either of those are fine. It doesn't really matter to me. For clarity's sake, I'll use this one just so you could see how it might be used. So remember, a general term for any term of an arithmetic sequence would be a sub n is equal to my first term plus your common difference times n minus 1, right? So you're essentially adding your common difference n minus 1 times. So if I want to find my 10th term, for example, I can take the first term, 28, and add that common difference of 6, n minus 1 times, or 9 times. So if I evaluate that, the 10th term of this series, or excuse me, of this sequence, would be 82. So if I wanted to use this sum formula here, the 10th partial sum would be 10, the number of terms, times my first term, which is 28, plus my 10th term divided by 2. So if I evaluate that in my calculator, that should be, I think, 550. If I wanted to do that in sigma notation, I could. I would just do capital sigma, right, from n equals 1 to 10 of that general term, which is 28 plus 6 times n minus 1. And if you type this into your calculator, you'll get the exact same answer, so it doesn't matter to me. If you don't remember where that sum button is on your calculator, if you hit the math button, which is right under alpha, if you go all the way down to 0, there's a summation button, and you can type it in from there. Now, instead of n, I'll just use x here because that's a little bit easier to access. Doesn't matter what letter you use, though, as long as you're consistent. And if I type that in, almost like a magic trick, it just spits out the answer. So either of those are fine, but you do need to know this formula and you do need to know how to use it. So for something like B, that's a bit trivial. If you know where that button is in your calculator, you can simply just type that in. For a geometric series, however, it's a similar process, but the formula that we're going to use looks a little bit different. Remember, the formula for the sum of a finite geometric series is your first term times 1 minus your common ratio raised to the n, where n is the number of terms, divided by 1 minus r. So I want to identify a common ratio first, right, because my first term is pretty obvious there. But to get from -1 to 0.3, and then from 0.3 to -0.09, my common ratio must be some negative number. And to find it, you can divide any two consecutive terms. So if I divide 0.3 by -1, or if I divide -0.09 by 0.3, you'll get the same answer. It's going to be -0.3. That's our common ratio. So again, I'm going to use this formula here. If you wanted to do this in sigma notation, you're more than welcome to, but again, you still need to know how to use this formula. So the sum of the first 10 terms would be my first term, -1, times 1 minus my common ratio, keep in mind that's a negative number, raised to the 10th, divided by 1 minus -0.3. Of course, I would never write it like that. It's probably a little easier just to write it as a plus. And when you type this in, I'd recommend you type it into your calculator as a fraction. I don't say what around to here, so in this case, let's say to the nearest hundredth. I believe that should be -0.77 around there. right? On a test, you'd have specific rounding instructions, so don't stress about that. Now, what if I wanted to find the sum of the first 8 terms of a geometric series where the third term was negative 4.5 and my common ratio was instead 1.5? Well, that's a little bit tougher, because if you think about one of the formulas we could use here, yes, I know the common ratio, yes, I know the number of terms, but I don't yet know the first term. Well, that's not a huge issue, right? Because if we think about how a geometric sequence is set up, right, where this is my first term, this is my second term, this is my first term, my third term. To get from my second term to my third term, I'd multiply by 1.5, right? Same deal from my first term to my second term. So if I wanted to reverse that process, I could simply divide by 1.5 twice. So if I want to figure out what my first term is, super easy to do that. I can do negative 4.5 divided by 1.5. So that's my second term. And then if I do it one more time, I get back to my first term, which should be negative 2. So I'm not going to take the time to type this into my calculator, but the setup for this would be the sum of the first 8 terms would be my first term, negative 2, times 1 minus my common ratio, raised to the 8th power, divided by 1 minus that common ratio there. And I'm pretty sure if you type this into your calculator, that should be somewhere in the ballpark of negative 98.52. But what if I wanted to express a series using sigma notation specifically, right? I would need to find some general term or the explicit rule to represent all of the terms in the corresponding series. So I notice that I'm doubling every time here. So this is a geometric series. And to find the general term in a geometric series, I could use the formula for a geometric sequence, right? That's the first term times your common ratio raised to the n minus 1. Okay, well, problem is, if I'm thinking about how to write this in sigma notation, I'm going to sum from my first term to currently I don't know what term. So your first task is to figure out what term number would get me 2048. And that's where this rule can come in, right? Because I know my nth term could be 2048. My first term in this case is 4, but my common ratio is 2. So if I wanted to find what n value would make my term 2048, I can simply solve this equation. So if I divide out the 4, I've got 512 equals 2 to the n minus 1. And then if I either rewrite this in log form, if I take the log of both sides, I could have the ln of 512 is equal to n minus 1 times the ln of 2. Right? Keep in mind, if I take a natural log or any log of both sides, I could bring that exponent down as multiplication. And then, to solve for n, I would have to divide out the natural log of 2, but I'd also have to add that 1 over, right? So if I do that, I'd get an n value of 10 here. So if I wanted to express this series in sigma notation, it would be sum from n equals 1 to 10 now of the general term 4 times 2 to the n minus 1. So this is what the series is represented as in sigma notation, and if I wanted to find that 10th partial sum, you could just type that into your calculator, or if you wanted to, you could use the geometric series formula, but in this case, there'd be no reason to if we already have it in sigma notation. So for number 4, here's an application where it says Megan just started a running plan where she runs 8 miles in the first week and then increases the number of miles she runs by 5% each week. If she keeps up this plan for 19 weeks, how many total miles would Megan have run to the nearest whole number? Now keep in mind they're asking for a total. They want me to add up week 1, week 2, week 3, all the way up to week 19. That's why this is representing a series and I'm not finding a particular term in a sequence because they're asking for the total of all of these. So if she increases by 5% each week, that means that she's starting at 8 miles and then multiplying that by 1.05 over and over and over again. That to me sounds like a geometric series. So I'm going to write a general term for a geometric sequence, which this expression right here would represent how many miles she runs in each particular week. So if I plug in n equals 10, for example, that would get me how many miles she runs in the 10th week. But to find everything from 1 to 19, I could either use this formula again, or I could use sigma notation. I'll use this formula just since we have all the information here, right? To find the 19th partial sum, I would do 8 times 1 minus, keep in mind my common ratio is 1.05, right? It's not 0.05, it's what I multiply by to get to the next term. So it's not a rate, it's a common ratio between consecutive terms. It's different from a rate of increase. And in this case, should be approximately 244 miles that she'll run over the course of those 19 weeks. So consider another application where Brian deposits 1 cent into an empty non-interest bearing account on the first day of the month, and he additionally deposited 3 cents on the second day, 9 cents on the third day, and 27 cents on the fourth day, and so on and so forth. Assuming he continues this pattern, what would the total amount of money in the account be by the end of the 20th day if the pattern continued? Now, again, we're representing a total, so this is a series, and given that he's tripling his amounts that he's depositing, I would say this represents a geometric series, right? That he starts with 0.1, and then he comes back and he puts in 3 cents, and then he comes back and he puts in 9 cents and 27 cents, and so on and so forth. You'll notice I've represented these as the number of dollars, right? Because 1 cent is a penny, it's 1/100th of a dollar. So if I want to know how much money, they didn't specify a unit, but a lot of times we want to leave that in dollars. So my first term is 0.01, but my common ratio looks like it's 3, that I'm tripling every time. So if I make those substitutions into this formula for how much he'd have at the end of the 20th day after he makes that 20th deposit, in this case, I don't think he'd be able to keep up this pattern for 20 days given how large this does grow. But if you evaluate this in your calculator, he would end up with an astronomical $17,433,922 and change, right? I'm rounding to the nearest dollar there, but I think that is an unrealistic pattern for him to keep up. But should that pattern continue, that's how much he'd end up with. For number 6. The first term of a geometric series is 8, and the fourth term is 2016. What is the sum of the first 12 terms of the corresponding series? Well, this is actually quite similar to, let me find it right here, the one that we did previously where, which one was it? Oh, this one right here, where I didn't know what the first term was, but I was given the common ratio. This is a similar setup, but now I don't know the common ratio, and I need to figure that out. Well, you could use the same logic, or you could try to use the explicit rule for a geometric sequence. Now, I always like to write it out visually. It helps me a little bit, where the first term is 8, and my fourth term is 216. Because one of the ways you could set this up is you could say, okay, well, if I multiply by once, twice, 3 times, using my common ratio, I should get from 8 to 216. So I could set up this equation right here to solve for my common ratio. Alternatively, if I use the explicit rule that we have on the left-hand side here, you can do the same thing where you say, okay, my nth term is 216, my first term is 8, I don't know what my common ratio is, right? So I'll leave that as R. But if 216 is the fourth term, then I'd plug in 4 for n. And notice that you actually do end up with the exact same equation. So there's many ways to interpret this. Pick one way and stick with it. I'm going to solve the one we have over here, right? If I divide out the 8 216 divided by 8 is 27. And then if I take a cube root, or alternatively, you could raise both sides to the 1/3 power, we get that our common ratio here is 3. So again, you should substitute into the geometric series formula. The answer you should get when you do that, finding the sum of the first 12 terms, should be 2,125,760. Now for each of these, I want to determine if these series converge or diverge. And if it does converge, I want to give the sum. Well, bear in mind that if a series converges, specifically a geometric series of infinite length, then it would converge to the first term divided by 1 minus the common ratio, right? We derived that in class. So looking at this first series here, 1/5, 1/25, 1/125th, that looks to me like it is in fact a geometric series, right? I'm multiplying by a fifth every time. So it is a geometric series. And we've established that this formula will work for a geometric series anytime your common ratio is between -1 and 1, or if the absolute value of that common ratio is less than 1. Essentially, that ensures that the terms will get smaller and smaller and approach 0, so that you're adding smaller and smaller parts so that eventually the pieces you add are so small that they're insignificant. Right? So given that we have that this does in fact converge, since your common ratio is 1/5, that's less than 1, I can substitute into that formula and have that be the sum. Notice I don't need a subscript here because this is the sum of infinitely many terms. Would be 1/5 divided by 1 minus 1/5, where, if you wanted to type that into your calculator, you could, but, of course, this is 1/5 divided by 5/5 minus 1/5, which should be 4/5. And if I'm dividing two fractions, right, I can multiply by the reciprocal, so I could change this to 1/5 times 5 over 4. The 5s would reduce to 1, and I would just be left with 1/4 or 0.25. Yes, you can plug it into your calculator, but it's always nice to remember how those fraction rules work. Now for B, this series is represented in sigma notation, and I think very clearly this is going to diverge, given that it is a geometric series and that 5/4 common ratio is greater than 1. So if you list out the first couple of terms, you might notice that that series is growing without bound. Now for the third one here, C, this is a little bit of a peculiar case because that 18 throws things off a little bit. But if I just ignore it, and if I look from the 2 onward, I think that does look like a converging geometric series, right? Where that's a geometric series with a common ratio that's 1/2, right? I'm halving over and over again. So I can instead think about the series in my head as 18 plus, the sum from n equals 1 to infinity of 2 times 1/2 to the n minus 1. That's just the general term for that geometric sequence, and I put it in sigma notation to get me the series. So if this is 18 plus some converging geometric series, I would say this series does in fact converge, because this part right here is some finite number. So that would be, 18 plus whatever that sum is, which is my first term divided by 1 minus my common ratio. So that's the same thing as 18 plus 4, which would just be 22. So if you sum up all the terms of the series, they should sum to 22. And D looks to me like it also does converge. The only thing you got to be careful about is that, when we're using this formula, I first need to establish what the first term is. I think very clearly the common ratio is 0.2 there. But if I start indexing at t equals 1, when I plug in 1 for t there, my first term is actually 5 times 0.2, or -1. So keep that in mind. So this series would converge to -1 divided by 1 minus 0.2. That's our common ratio there. That would be -1.25. Okay, so for number 8, it says a ball is dropped from a height of 32 feet, and it bounces and rebounds 80% of the height from which it was falling. What is the total downward distance the ball will travel? So total, and it's specifying downward distance, so keep that in mind. So even though when a ball bounces, it goes up and then back down, I only want the downward distance. That would actually simplify things here a little bit. So let's consider what's happening here. We've got somebody drops a ball from a height of 32 feet, right? So it comes down and it initially travels 32 feet downward, right? Bounces back up, rebounds only to 80% of the height, and then it will continue that and so on and so forth. So to get from this height to my next downward height, I would just multiply by 0.80 or 0.8, right? That's how I get 80% of a number. So this is representing a geometric series, but you might notice that it hasn't told me how many terms to sum up. It just asked me what is the total downward distance, because eventually, imagine if you drop a ball, it'll dribble and get smaller and smaller and smaller, but at some point, it will eventually reach the ground, or at the very least, be moving so infinitesimally small from the ground that that distance won't make much of a difference. I think it performs something very similar to our last series, where I can just use that infinite geometric series formula, given that I have what the starting height is, and I have what the common ratio is. So if I don't want to find the sum of the first 5 terms, the sum of the first 10 terms, I want to find the sum of all of them. That is an infinite geometric series. And since our common ratio is less than 1 and greater than -1, I know for a fact that this will converge. So it will travel a total of 160 feet downward. Now, bear in mind there's lots of ways that I could change this question, right? If I wanted the upward distance, bear in mind that that 32 feet wouldn't count towards the upward distance. I'd have to start counting here. And if I wanted to find the total upward and downward distance, maybe I'd add 2 series together to try to figure that out. Okay, so let's try a proof by induction now. Right, I want to prove that this statement is true for all natural numbers n. That if I sum 1 cubed, 2 cubed, 3 cubed, all the way up to n cubed, that should be the same as n squared times n plus 1 squared divided by 4. All of these steps are always going to be in the same order. The only thing that's going to change is your induction step. So my first case is going to be base case. Right, so I want to establish that this works for at least one value, right? Because if it doesn't work at all, then I'm not proving anything. So I want to check to see that 1 cubed is the same thing as 1 squared times 1 plus 1 squared divided by 4. Well, let's see. 1 squared is 1. 1 plus 1 is 2. 2 squared is 4. I think that's just 4 divided by 4. And yes, 1 is in fact equal to 1, so that passes the base case. Now, my second step is my induction hypothesis, right? I want to assume that it's true for n equals k. So I'm going to assume true for n equals k. What that means is that I'm going to assume that there's some arbitrary natural number that this works for, and I'm going to use that as a springboard to prove that it works for the next case right afterwards. So essentially, I'm just going to take this rule, and everywhere there's an n, I'm going to replace that with k. All right, so plus k cubed should equal k squared times k plus 1 squared divided by 4. And that's what I'm going to assume to be true, and I'm going to use that to prove that the next case is true. So what I want to show is I want to show that the statement is true for the next case, n equals k plus 1, that if it is true for k, then the next one would also be true. So I want to write what I'm trying to get to be true. essentially I'm going to rewrite this now, but replacing the n with k plus 1 instead of just k. So I'll write that series as 1 cubed plus 2 cubed plus dot 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 plus, and it's going to go up to k cubed, but it's going to go one term more, right? It's going to go to k plus 1 cubed. That's what the left-hand side of that series looks like. And now I'm including that as well, instead of just writing it in the dot 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 part, because I want to show that it's actually got a lot in common with what I'm assuming to be true in that induction hypothesis. So now I want to show that that's true for k plus 1 squared times k plus 1 plus 1, or k plus 2 squared divided by 4. This is my goal here. This is what I want to show is true anytime that step is true right there. So in order to do that, I'm going to somehow algebraically manipulate this right here to get it to look like that right there. So this is our induction step now, right? The step that's going to change for all of these because the algebra is going to look a little different. We're going to use n equals k being true to imply that n equals k plus 1 is also true. That's my goal here. So essentially, I am assuming that this is true. So I'm allowed to manipulate this however I see fit, right? I can apply any properties of equality that I want because I'm assuming that it's a true equation. And I notice that this series that I'm trying to get only has one more term, right? It's got that plus k plus 1 cubed. So what I'm going to do is I'm going to take that left-hand side there, and I'm going to add k plus 1 cubed to both sides. So 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus k cubed. Notice I'm leaving space there. It's equal to k squared times k plus 1 squared divided by 4. Now, please note that I'm assuming that this is true, so I could do whatever I want to it, but I need to apply a property of equality consistently. So if I choose to add k plus 1 cubed to the left-hand side, I also need to do that to the right-hand side, right? If I add something to one side of the equal sign, to maintain equality, I need to add that same quantity to the other side. Now, again, the reason I'm choosing to do that is because that would get this left-hand side to match exactly what I want that left-hand side to look like. So what I hope here is that algebraically, as I manipulate that right-hand side, it eventually takes the form of k plus 1 squared times k plus 2 squared divided by 4. And provided you are careful with your algebra, it should, right? You're trying to prove that something is true. So it's already been proven by mathematicians many years ago. We're simply using our algebra skills to get there. Okay, so there's nothing we got to do with the left-hand side, but I've got to clean up that right-hand side. First thing might be to be multiplying that expression by 4 over 4, so that I could rewrite these as one fraction to make it k squared plus k plus 1 squared plus 4 times k plus 1 cubed divided by 4, right? Because they're all over the same denominator, I could write it as one fraction now. Now, there's a good way to do this and there's a bad way to do this. The worst thing you could do is start distributing, right? Keep in mind your goal. Your goal is to get it to look like k plus 1 squared times k plus 2 squared divided by 4. I've already got the divided by 4, but it should be eventually factored nicely. So I noticed something about the two things I have in the numerator here. Like when you chunk these in your head, I want you to think about that as one thing and then that as a separate thing, right? Because they're linked by addition. And I do notice they actually have something in common. They both have k plus 1, but better than that, they both have k plus 1 squared, right? This has a k plus 1 squared, and this has k plus 1 cubed. So they both have at least 2 k plus 1s. So I can actually factor that out as a GCF. If I factor it out as a GCF from the first thing, I would just be left with k squared, right? Because this entire first term is k squared times k plus 1 squared. But if I factor it out from my second thing, I'd still have that 4 being multiplied, and I would still have 1k plus 1, because there's 3 of them there, and I'm only pulling out 2 of them. And now I have a much simpler expression to look at. I factored out k plus 1 squared as a GCF, and as I look back to what I want to show, I notice I'm actually pretty darn close of, I've got that k plus 1 squared out in front already, so I really just need to clean up that k squared plus 4 times k plus 1. So if I do that, all right, let's see. I'd have k squared plus 4k plus 4. Oh my gosh, that looks like a factorable quadratic, right? I could ask myself what adds to 4 and multiplies to 4. I think that should be 2 and 2. Oh, man. All right, please hold, please hold. Come on, one note, come on, we're almost there. All right, so I've got the k plus 1 squared, and then I've got k plus 2 times k plus 2, all divided by 4, which, if I then clean that up, is equal to k plus 1 squared times k plus 2 squared, divided by 4, which is exactly what I wanted to get it to look like, right? So we essentially, to recap, just showed that that was true for n equals, oh, excuse me, this one right here. We assumed it was true for n equals k, and we were able to prove that it's true for n equals k plus 1. So therefore, this statement must be true for all natural numbers. So you just need to write some sort of concluding statement, right? So since the statement is true for n equals k plus 1, anytime it is true for n equals k, it must be true for all natural numbers n. That's what a proof by induction will always look like. There'll be a base case to start, then your induction hypothesis, and then, assuming it's true for n equals k, using that to get n equals k plus 1 to also be true. That's your induction step. So the logic is, you proved that it's true for n equals 1. And you also prove that if it is true for some number, then it must be true for the number right after that. So, by that logic, if it's true for n equals 1, it must then be true for the number right after that, n equals 2. But also, I proved that it's true arbitrarily for the next case every time. So if it's true for n equals 2, then it must be true for the case immediately afterwards, n equals 3. And if it's true for n equals 3, it must be true for n equals 4, and so on and so forth. That's the benefit of a proof by induction, right? It proves it for infinitely many cases simply by looking at a specific case. So I will leave the other one for you to try on your own, which was this one right here. And the answers to that written up is on Google Classroom as well, so make sure to take a look at that at some point. Okay, for number 10 here. The whole square pictured has a base and altitude of 1 inch. So both of the sides of this square are 1 inch long. All right, so like right there, that's 1 inch from there to there, and that's 1 inch from there to there as well. I want to find the area of the shaded red part remaining after the indicated squares have been removed. So all those white squares have been removed, where the first white square has a base of 1/2 inch. Now keep in mind it's a square, so that means the base and height are the same. And we're going to assume this pattern continues. So that's 1/2 inch by 1/2 inch. So then this would be 1/4 inch by 1/4 inch. And this would be 1/16 inch by 1/16 inch, and so on and so forth. I implore you to try to think about this on your own instead of just watching this video for a solution, because it's really interesting when you start to think about it. Because the entire area of this square, right, total area, is 1 square inch, right? 1 times 1. That's how I find the area of a square, base times height. So I would need to figure out what the area of the white squares are and then subtract that from the entire figure. So it would help to find what a few of them would be first, right? That first square that I've removed would be 1/2 times 1/2, or 1/4 square inches. The next area would be 1/4 times 1/4, which would be 1/16, right? So let me write that out. The first area would be 1/4. The next area that I'm removing is 1/16. The next area I'm removing would be 1/16 times 1/16. Hold on, I think I might have missed. Oh, that should be, excuse me, right? That should be 1/8 times 1/8, right? I'm halving the length of these sides every time. So 1/8 times 1/8 would be, what, 1/64th, and so on and so forth. So I'm trying to notice a pattern in these areas that I'm removing, because I would like to add up all of those empty spaces and then subtract that from 1. Well, there's infinitely many of them, but I do believe this is a geometric series, right? 1/4 to 1/16 is just multiplying by 1/4. 1/16 times 1/64 is again multiplying by 1/4. So this geometric series has a first term of 1/4 and a common ratio of 1/4 and is infinitely long. And since that ratio is between -1 and 1, I know that it converges, and I know it will converge to my first term divided by 1 minus my common ratio, or 1/4 divided by 1 minus 1/4, which would be 1/3. So that represents all of the white area that I've removed. And if my total area altogether was 1 square inch, and I've removed 1/3 of a square inch from it, the remaining red area must instead be 2/3 of a square inch. So this really is another application of an infinite geometric series. For number 11 here, Jasmine decides to put $100 in a savings account each month, and the account pays a 3% annual interest rate compounded monthly. How much money, S, would Jasmine have after 1 year? Well, that's going to be 12 months of depositing that $100. So it should take the form of this right here, right? Given that it's a finite geometric series. But bear in mind that sometimes you might see this formula written like this instead. If I distribute that first term into my parentheses there, I bring that up because I notice 2 of my answer choices look like that. Now I could immediately rule out A and C, because Jasmine's going back to the bank and she's putting in $100 each month. So she's putting $100 in for the first month, going back in the second month, putting $100 in. That's what makes this a series rather than some sort of sequence, right? Actually, C would get the amount that the first $100 is worth after 12 months, but I'm not interested in that, right? I want to add up all of these individual deposits, all of which are earning a different amount of interest. Now, to find my common ratio R, you might want to adhere to the compound interest formula, where this number right here controls what you're multiplying that principal by over and over again each time you earn that interest every month, right? Even though it's a 3% annual interest rate, my common ratio R for this formula is not going to match that 3%, right? Because this represents what I multiply by, not what the interest rate is, right? So this number here would actually be 1 plus 0.03 divided by 12, right? Because you're getting a 12th of that 3% every single month. Or if I clean that up, 1.0025. So that's actually my common ratio. And since my first term is 100, this answer choice B would be the corresponding series for this financial application. Financial applications are very popular ways to show an application of a geometric series because you'll have money at some point, and this is exactly how your money will grow over time if you make consistent contributions all of the same amount. So let me give you just one more financial example. Let's say Pablo finds a bank account that offers him a 6% interest rate compounded monthly. Right, so that means every month he's earning 1 plus 0.06 divided by 12, a twelfth of that interest rate. He wants to make recurring investments of the same amount each month. He is planning to save for 2 years. Now, bear in mind, right, this is my common ratio between my terms. If he's saving for 2 years, since our interest is compounded monthly, that's actually 24 terms I would have to look at in whatever this series is. And his goal is to save up for a new laptop that costs $1,500. Determine algebraically how much he would need to save each month to the nearest dollar to reach his goal. So I know what the sum of the first 24 terms of this series should be. I want it to be 1,500. If I think about my geometric series formula, right, for the sum of a finite geometric series, I know the common ratio, I know the number of terms, I actually know what the final sum should be. I just don't know what that first contribution should be so that he earns $1,500 over the course of this 24-month period. So if I have all those pieces and I'm just missing one, I can make some appropriate substitutions, right? I can set the total sum to be 1,500 equal to my first term, which that's what I'm looking for, times 1 minus my common ratio raised to the 24th, because again, this is 2 years, but it's a monthly interest rate, divided by 1 minus 1 plus 0.06 divided by 12. And this is the equation you would need to solve in order to get that, how much he would need to save each month to the nearest dollar. So let me show you what that would look like if we clean that up. If I multiply that denominator over to the other side, so I'm going to take this, multiply to the 1,500, I would get negative 7.5 equals my first term times 1 minus 1 plus 0.06 divided by 12 raised to the 24th. And then all I would have to do is just divide this number out from both sides. And that should get me approximately how much I need to save, or excuse me, how much Pablo needs to save each month to save up for this brand new laptop. So I think it's about like $58.98, which if I'm rounding to the nearest dollar would just be about $59. So that could be another example of a financial application here.